Alright, let's look at these together. So the first one I left you to do, we have CD is from 0 to 2, so that's a distance of 2. And then A to B is from negative 2 to positive 3. How far is that? Negative 2 to positive 3. Distance of 5. Because there's 2 that direction and 3 that direction. So 2 plus 3 is 5 total, right? So 2/5, we can't reduce that, but we can do a percentage for it is 40%, because it would be 0.4, right? Okay, tell me what you got on the next one. Okay, maybe we just do it slowly. So this one's at negative 5, because it's between negative 10 and 0. So how long is CD? Kenny, how long is CD? From negative 5 to positive 10. Thank you, Kenny. Tila, how long is it from A to B? Yep, 30 is correct. So can we reduce that fraction? So what's the chance on that one? 1/2 or a 50% chance. Okay, from C to D, how long is it? It's not 2 because C is not at 0. Yeah, it's only 1. And then from A to B, from negative 1 to positive 4 is 5. Good. So 1/5, which is what percentage? Brenda, did you get the percent for that one? So Spencer wants to be called Brenda. And we got 20%. Good. Okay. Now the whole reason we learned this method of using a little segment to figure out a probability is that when you're dealing with time, time can be represented with a segment. Okay? So let's do the next problem, which is a little story problem, using a segment. If you arrive more than 20 minutes late for class, the teacher can mark you absent. Classes are about 90 minutes long. Suppose Sam arrives late to school but has no idea what time it is. What is the probability that he will arrive more than 20 minutes after the beginning of one of his classes? So if I'm going to use a segment to represent a class period, how long would my segment need to be? How long is a class period? 90. So I need a segment that represents what? No, just one period would be fine. So it starts at time 0 and ends at time 90, okay? Well, what happens at 20 minutes into class? Yeah, starting from 0 to 20, a student will be marked tardy, but from 20 to 90, a student would be marked absent even if they come. Does that mean they shouldn't come at all? I think there's still things you can learn even if you're officially on the records absent, right? So I think it's still to your benefit to go, but just be aware of the rule. That's just what it is. Okay, so the question is, what is the probability he will arrive more than 20 minutes and therefore be marked as an absence? Well, here's what we do is we want to find how long this segment is right here. This is when he would be marked absent. So how long is that part of our segment? Austin. Yes, it is a length of 70 minutes long where he would be marked absent. 70 out of how many minutes total? Out of 90 minutes total. So if he arrives to school at a random time, the probability that he will be marked absent rather than merely tardy is what? We have the 7 over 9. I reduced 70 over 90 to 7 over 9, but let's find a percent because that makes more sense to my brain. Does it round up? Because I think my other class said 78. Okay, let's just call it 78% if we round it up. So it's a greater chance he'll be absent than tardy if he doesn't know exactly what time it is when he's arriving, right? Okay, so that's using segments to solve probability problems. So segments are something we've learned this year in geometry, right? So you're going to use that anytime you have a problem involving time. The next group of problems involves area. However, depending on the problem, we don't always have to find the area. For example, this one is triangles, so we might want to find the area of each triangle. However, we don't need to find the area of each triangle because each of the triangles in this picture are the same size. So we can do this problem like we did our spinner problem earlier, right? We want to find the probability by doing shaded area divided by the total area. Like pretend that these are little dart boards and we want to figure out the probability of hitting the shaded area with a dart. And we're not taking skill into account at all. We're just saying if we hit the dartboard, which would be lucky for me to just hit it at all, then what are the chances that we're actually going to make it in the area we want it to make it in, right? Assuming we have no skill in getting it to that location. It's just random. So on this one, without even having to find area, how can we do it? Spencer?
You can triangles in it, and then there's 3 shaded and 2 non-shaded.
Okay, so what do I do with those numbers?
It'd be 3 over 5.
Good. I was afraid when you said there were 2 non-shaded that you might accidentally tell me it would be 3 over 2. 3 shaded and 2 non-shaded. But he did it perfectly. He told me there were 3 shaded, and then there were 2 non-shaded, which gives us a total of what area? Or total of how many triangles? 5 of them, right? So the probability is 3 out of 5. Now go ahead and just practice finding that percent for me. Austin? Did you say 80? It's not. Try again. Angel. Good job. So 60% for that one. Okay. This one we could also use area. We could use the areas that we just barely learned about. Look, there's a sector and there's a circle. We could do the area of the sector divided by the area of the entire circle. However, we don't need to do areas. We can just do it with the angles. Because we know that the shaded angle, the angle of the shaded sector is 130. What's the angle of the entire circle? 360. So instead of having to actually do the areas and divide them, we will get exactly the same ratio just by using the angles because they will have the same radius, and so it would be the same proportional area. So if the shaded area is 130 degrees, then the probability of hitting that shaded area would be 130 divided by the 360 degrees that are in the entire circle. Can we reduce that fraction? What would 130 over 360 reduce to? Because you should always reduce it if you can. It's pretty easy to reduce because you can just get rid of the zeros. So it's just 13 over 36. And that one doesn't divide down any further unless you want to find the decimal, which is always good. Find the decimal for me. 13 divided by 36 or 130 divided by 360. You'll get the same answer either way. What did you get? Good, 36-ish percent. 36.1. Sounds good to me. Okay, so this one was pretty easy. We could just count the triangles. This one was pretty easy because we could just use the angle.
Teachers, please excuse this interruption. At this time, would you excuse all track members to board the bus for their meet today immediately? All track members, please go immediately to the bus in the front of the school. Thank you.
Okay, I just wanted to quickly show you your actual homework. I forgot to tell you this before. Your homework is in the book. It's page 350 and 357. But because the notes I was giving you today only covered one side of the paper, guess what I put on the other side of the paper? The book assignment is on the other side. So let's just quickly look at it. We did a problem like number 1. That one's easy. Number 2 is like the one we just barely did, only there's a major difference I want to talk about really fast. All of them. All but the very, very last one. Okay. Okay, listen please. I just want to point out something that's tricky in number 2 that's different from the one we just did. In the one we just did, the shaded area was the angle they gave us. Look now what angle they've given us. The angle is the non-shaded area. So I saw Oliver say what we should do, which is what? Subtract it from what? Take 360 and subtract 120, and then that's the angle you will use. Divide by 360, right? Okay, just a warning. Now the next example I'm going to do is an example that will help you with these two problems. It's different but similar. So please pay attention to the next problem very carefully so that you'll be prepared to do these two on your assignment. Okay? The next problem, we really actually do need to use areas. We really are going to use areas. So